Okay, so there's only a couple cases that we can easily calculate the inductance of an object. The simplest one to deal with is inductance of a long solenoid. So, imagine we have a coil with N turns, okay, and some length L, okay. If we, again, no coil is really infinitely long. But if we assume that this is quite long compared to its radial dimension, say, call this dimension here, let me draw a little bit better here. So I have my solenoid and I'm winding turns on it. Okay, I'll call this dimension A. And if A is very small compared to L, the field inside of it will approximately be the same as an infinitely long solenoid. We saw how to calculate that with Ampere's law. So B is going to be mu naught N times I for a very long solenoid, okay, where N is the number of turns per unit length, so N is N over L, okay. So if I imagine now driving a current through this coil that might change with time, so I'll have a battery here, and I'm going to have my coil and drive a current through it. As I try to change the current, there will be a back EMF, okay, because the current that's being driven here will generate magnetic field that goes through the coil. Try to draw that better here. Okay, so you have magnetic fields that are created that are associated with this coil, and as the current changes, the magnetic field will change with time. That will generate an electric field within the coil that will generate a back EMF that will oppose the change to the current. Okay, and we, from the last video, we can write that back EMF due to the magnetic field changes as minus L di dt. Okay, so the minus here comes from Lenz's law. Basically, the EMF will try to oppose the changes, and because the changes are associated with the current actually flowing in the coil, it's a little easier to figure out the direction of the EMF. It's always going to oppose the changes in the current. So it's going to try to drive a current to oppose the changes in the existing current. Okay. All right, so we're going to calculate L for this coil. And the definition of L is just that the L times the current through the coil is equal to the number of turns times the flux that goes through a single turn in the coil. Okay. All right, and so because the magnetic field is uniform in this case, the flux through one turn is just going to be the area of one turn, which is going to be pi a squared times the magnetic field that's going through that surface, which is going to be mu naught N times I. Okay. So you see we have now, can figure out what L is from this. We have L is going to be mu naught N times N, little n, times pi a squared. Okay? Or if I, oh, here I have to be careful. I said big L up here. Let's call this, because I'm using inductance for big L. So let me get rid of that and call it little l. Okay, so looking up here. So now if I can write this, let me go to the next page here. I can write this now in terms of the, well, I can do one of two things. I can do the following. I can say that it goes like the number of turns squared over the length, okay, times pi a squared. Equivalently, it's the number of turns per unit length squared times the length, pi a squared. Okay, so here's an example of a calculation of the inductance. In most coils, you're going to measure it. You make the coil, you measure the inductance, and then you can use that then as you plug it into a circuit. In this case, we can calculate it. You see, it depends only on geometry, the number of turns, the length, the radius. There's no dependence on anything else, no dependence on the actual current. Okay, so this is really a geometric factor that tells you something about when I drive current in a coil, how much flux shows up how much flux does the coil surround because of its own current. Okay. All right. So that's one quick example of how to calculate inductance.